Good morning. Infinite Series, Part 6, Part 2. We last left off in our flowchart. We had done the 3 easy questions, which are, is it geometric? Is it p-series? Are the terms approaching 0? None of those have helped us, so now we ask ourselves, are there negative terms? If there are, we throw them away and we go to the big rectangle. So today I want to talk to you about what's in that big rectangle. Normally there are 4 tests in that big rectangle, and we would have to decide which one to use, or AP would tell us which one to use. This year, thanks to the virus, there's only 1 test in the big rectangle. Frankly, it's the test that we would have used 99% of the time anyway, which is probably why it's the one they left behind. It's my favorite. It's everyone's favorite. So let's talk about it. It's called the ratio test. My technology has been not nice to me today, so this could get interesting. All right, here's the ratio test. I consider it the best test ever. And it is. So there's that. All right, so the ratio test, what it does, not shockingly, is that it puts 2 terms of a series into a ratio. And then we look at what happens generically, right? So in terms of n. So this ratio right here is your nth term, which is what's given to you in the series. Like it's written in terms of n. And then the top of the ratio here is your n plus 1th term, which is literally the same expression with all the n's replaced with n plus 1's. So what you're looking at here is the ratio of 2 consecutive terms. Now, one thing we know about convergence is that as you go towards infinity, or as your n gets bigger and bigger, that ratio better be less than 1. Because if it's not less than 1, then that means that your terms are getting bigger. And if your terms are getting bigger, you should have caught that with the nth term test. Just saying. Okay, so sometimes though, it's not really evident. So in the beginning, we looked at sum with partial sums where it was like, it's too close to call. So here's our ratio test. Here's the way it goes. You set it up, you take the term that's it's given to you in your series, you rewrite that same term in terms of n plus 1, and you take the limit of that expression as n approaches infinity, and you see what happens. One of 3 things is going to happen. Oh, I forgot to mention. I always forget to mention it. That's why I have that star there. Technically, the ratio test has absolute value signs in here. Because, of course, you're not allowed to have any negative terms. So the absolute value signs kind of catch that for us. It's also going to help us when it comes to radius or finding an interval of convergence, the absolute value signs. However, usually we don't keep writing them throughout. And since there's no negative terms, people don't really write them in the beginning either. But it does become important to us when we're finding interval of convergence. So it's worth mentioning that technically there are absolute value signs there. Okay, so like I was saying, one of 3 things is going to happen. The best thing that could happen for us is that what comes out is the number that comes out of this series is less than 1. If it's less than 1, that's convergence, kind of like geometrics. Right? If it's less than 1, that means your terms were getting smaller, and they were getting smaller quickly enough that as you approached infinity, this limit came out to less than 1. So that's good news. If it comes out greater than 1, the series diverges. The only way this test fails you is if it comes out to exactly 1. So if your limit comes out to exactly 1, you've got nothing and you have to try another test. I'm guessing they can't do that to us this year since there aren't any other tests. So that's good news, I guess. All right, so here's what I like about the ratio test. First things first, it's easy to use. You don't have to come up with any anything else, anything clever. You don't have to write an argument. You don't have to justify your answer. There's another test called the limit comparison test, where you have to find another series that you know about to compare it to. So you might say, well, I know that 1 over x squared converges, so let me compare it to that. I don't like that one, because you have to have another series to work with and hope that you're going to be able to simplify and stuff. Also, compared to the other ones, this one is really easy to interpret. It's either greater than 1 or it's less than 1, and that's the end of the story. And since that's kind of the same criteria as geometrics, it's kind of nice. The only kind of difference there is that in a geometric, if it's equal to 1, that's divergence, and here that would be inconclusive. Now, if your series is just a series with n's in it, this is going to give us a numerical answer, and we'll either say convergence, divergence, or inconclusive. If you have a series with x's in it, once you do the limit, instead of being left with a number, we're going to be left with an expression in terms of x. And that expression is going to help us find the interval of convergence. And the ratio test is the only test that will help us find an interval of convergence. So I always say that it's handy if they ask you for an interval of convergence. One of two things is happening. Either it's geometric, or you're supposed to be using the ratio test. Now, if you use the ratio test on a geometric series, it'll still work. It'll still give you the convergence. It's just a little more work than needs to be. And that whole like it coming out to 1 kind of really doesn't happen that often. So again, the ratio test every year is kind of the one that everybody goes to. Everybody tells me, like, top secret, I don't use any other test. No, nobody else does either. Okay, so let's try one. It says check the series for convergence. Now, I typed this one up because it's a lot of writing, and I wanted to make sure that the first time we go through this algebra, it's nice and clearly written for you. So I typed this one up, and then I'll make an attempt at handwriting the other ones. So the first thing you're going to do is set up your limit as n approaches infinity, and this is going to be the n plus 1th term over the nth term. Now, like I said, the term that they gave you in your series, this is your nth term. So all you really have to do is recopy it down into here. Now, it's probably a fraction, which is kind of obnoxious. You're sticking a fraction into a fraction, and in a minute, we're going to put another fraction in the numerator. It looks really, really ugly, but it simplifies really nicely. So don't be too intimidated by it. Okay, so I'm going to put my nth term here in the denominator, and then I'm going to rewrite my nth term, and I'm going to take out the n's and replace them with n plus 1s. Looks like that. I know. So notice 3 to the n became 3 to the n plus 1. N squared plus 3 became n plus 1 squared plus 3. Now again, that looks really, really bad. It's two fractions inside of another fraction, and we don't like fractions to begin with, so that looks not great. Right? Now, some people are better at simplifying in their minds. I am not one of those people. The first thing I do every time is invert and multiply. I take this denominator and I flip it and multiply so that I just have two fractions being multiplied and not two fractions being divided. So once I do that, it will look like this. So notice your numerator is here still in pink. My denominator has come out, it's multiplying, but now it's flipped over. Right. I haven't done any calculus yet. I'm just trying to get it so I can do some calculus. All right. So once it's here, I say simplify the heck out of it because you actually won't believe how nicely this simplifies down. So the first step towards simplifying it is I say to, well, two things. We're going to consider our constants and we're going to rearrange it. When I say consider your constants, I want you to remember back in chapter 2 when we were doing limits and we said, look, if you're approaching infinity, if you have like x plus 1, I don't care about the plus 1. So for example, this plus 3 right here, yeah, We're approaching infinity. I don't care about that plus 3. As n plus 1 squared, as n approaches infinity, this is going to be huge, and that plus 3 is not going to matter. So if you have things like plus 1, minus 1, plus 3, minus 3, you can pitch them in this step. The other thing that we're going to do is we're going to rearrange them. So currently I have 2 fractions. Each fraction has an n squared type. Oh, I forgot to cross out this plus 3. See you later, plus 3. Okay. Each one has like an n squared type term, and each one has a power of 3 type term. I'm going to rearrange it so that those terms are in fractions together. Right, so it's going to end up looking like this. So notice my n plus 1 squared is in a fraction with my n squared, and my 3 to the n is in a fraction with my 3 to the n plus 1. You don't have to write it like this. For me, it makes it really, really easy to see the simplification. So we talked, again, back in chapter 2 about how when you have something like this, this is a second power polynomial over a second power polynomial. This is going to go to 1. Now, your chapter 4 self might say, I'm going to use L'Hopital on that. I'm going to FOIL out that numerator and make it n squared plus 2n plus 1, and that's going to be infinity over infinity, so I'm going to L'Hopital it twice. You go right ahead. But also remember, there's a shortcut when you're approaching infinity with polynomials, that all you have to do is look at the first terms. All we care about when we're approaching infinity is n behavior, right? So since this is an n squared and this is an n squared, I can go like this with these other terms. They're not affecting the n behavior. N squared over n squared is 1, and this whole limit goes to 1. Disappears. Over here, I have a 3 to the n over a 3 to the n plus 1. So again, I think of that bottom as, oh, there's one more 3 down there than there is up top. You might want to think about it, and I feel like we've done this before. 3 to the n plus 1 is the same as 3 to the n times 3 to the 1. And if you do that, you can cancel those. So all of this mess simplifies down to the limit as x approaches infinity of 1 over 3 to the n. When you evaluate that limit as n goes to infinity, you get a 0. So, looked really ugly. We did some algebra simplification. We ended up with a really simple limit. More importantly, this answer, this number that we got, tells us whether or not the series converges or diverges. This number is less than 1. Therefore, it converges by the ratio test. Done. Easy peasy. Okay? Looks ugly. It's not too terrible. All right, let's do another one. Okay, so we want to know if it converges or diverges. We have a series that 1 over 2 to the n minus 1. So again, it's a series just in terms of n. So we'll start out, the limit as x approaches infinity. Oh, not x, n, sorry. As n approaches infinity. I'm going to do my x to the n term down here. And up top, my x to the n plus 1th term. So 1 over 2 to the n plus 1 minus 1. And then let's do an invert and multiply. So this turns into 1 over 2 to the n plus 1 minus 1 times 2 to the n minus 1 over 1. So all I did is I took this, I flipped it over, and brought it up as a multiplier. Because I don't want to have to deal with a fraction and a fraction. Once we do that, this one simplifies even better than the last one. I'm going to say, you know what, minus 1 as I approach infinity, I don't care about that. So I have 2 to the n, and I have 2 to the n plus 1, which very nicely simplifies to 1 over 2 to the n, which comes out to 0 again. And again, we say that is less than 1, therefore it converges by the ratio test. If I didn't mention this already in a previous video, it's really, really important to mention what test you're using.